We're going to spend 2 days on 5.5. So far, we only know how to take the antiderivative for power functions, trig functions, e to the x, and 1 over x. 1 over x is a type of power function in the sense that you can rewrite it as x to the power of a number, but it doesn't follow the power rule for antiderivatives, where when you add 1 and then divide by the new exponent, you would get the antiderivative. It would not be true for 1 over x because you'd get an undefined expression. So take a second and think about what the antiderivative or integral for 1 over x is. Don't forget those absolute value signs to account for negative x values. Today we're going to learn about the reverse or anti-chain rule. It's also known as U substitution. We'll talk more about that or why in just a moment, but we've learned chain rule for derivatives and we're going to learn the chain rule for integrals. So chain rule means that there's a composition of functions, meaning there's a function in a function. So g of x is inside a bigger function, f of x. It's called U substitution because it's easier to replace the function with a variable u. So we would let u equal g of x. So we're just replacing a function with a variable so that it's easier to work with. There's some other fine print about the criteria in that the inside function's derivative is continuous, and this is the notation for an antiderivative. But basically this is saying you can only take an integral if the composition of functions is multiplied with the derivative of the inside function. And its integral would be whatever the integral of the outside function is with the inside function left the way it is. That's a lot to process, I totally get, so it'll make more sense with an example. Here are some guidelines. So first, let's actually look at an example and then we'll go through the steps. So use substitution to find the antiderivative of this integral. So what you could technically do is multiply this out 4 times. That's a lot of multiplying out, and then distribute the 6x so that you have a polynomial or a bunch of power functions, and then you could use the power rule for integrals and take the antiderivative. But what you'll notice here is that this is a composition of functions, and this is the derivative of the inside function. Okay, so step 1 is to identify the inside function and call it u. You want to make sure that the derivative of the inside function is also part of the integrand. So our inside function is 3x squared plus 4. So I'm going to let u equal 3x squared plus 4. Its derivative should also be in the function, or in the integrand. Remember, integrand refers to the whole thing that's being integrated. So u prime, or du dx, equals 6x. That's the derivative of this, and it's in the integrand, which is good. Okay, so I'm going to rewrite the integral using u and du. So this integral is u to the 4th and 6x dx, that's what du is. So I'm going to say du equals 6x dx. So this is du. Okay, so I now know how to take the integral of u to the 4th. I would add 1 to the exponent and divide by the new exponent. And this should be plus c because it's an indefinite integral. So I took the integral with respect to u, And now I'm just going to plug g of x back in for u. So replace this with u, or replace u with 3x squared plus 4. All over 5 plus c. This is my antiderivative. And you can check this by taking the derivative, check, of your answer, just like we did when we first learned about antiderivative, when derivatives, when we were verifying. So if I were to take the derivative of this, I would use chain rule. So I would bring down the 5, subtract 1 from the new exponent, and then multiply by the derivative that's inside, and then the derivative of plus c. The derivative of a constant is 0. Whoops. And we end up with 3x squared plus 4 to the 4th times 6x, which is exactly my integrand. Okay, take a moment and try this antiderivative. So start by identifying your u, your inside function, and check that the derivative of the inside function is in the integrand. So the inside function here is x cubed minus 3. Its derivative is 3x squared, which is part of the integrand. So that means du equals 3x squared dx. So I can rewrite this integral as u to the second times du. Its antiderivative or integral is u cubed over 3 plus c. Don't forget the plus c. And if I replace the u with x cubed minus 3, I get my final answer. And you can leave it in factored form, totally fine. You can always check by taking the derivative, making sure to use chain rule, and see if it actually equals your original integrand. All right, let's do another one. So replace the inside function with u and check that the derivative of the inside function is in your integrand. So my inside function is x squared minus 5, and the derivative is 2x. Move the dx to the other side. So there's a bit of a problem here because only x is in the integrand. So I have my x and my dx, but I don't have my 1/2. So what I need to do is move the 2 to the other side. So if I divide by 2 on both sides, I'm actually going to write it as a 1/2 dx. So when I replace the x and the dx with du, I'm actually going to replace it with a 1/2 du. So my integral now becomes u, or square root of u, times 1/2 of du, which I'm going to rewrite as 1/2 u to the 1/2, and then take the integral. So the 1/2 stays in front, add 1 to the exponent, and then multiply by the reciprocal, or divide by the new exponent, plus c. So this becomes u to the 3/2 over 3 plus c, which is x squared minus 5 to the 3/2 plus c. And just to, sorry, there should be over 3 plus c. So just to clarify that a little bit more, or just to show that it does work, I'm going to take the derivative and show that it equals the original integrand. So if I took the derivative of the inside, or of the answer, I would get bring down the exponent, subtract 1 from the exponent, and then times the derivative of the inside. The 3's cancel out, the 2's cancel out, and I do get x and square root x squared minus 5. I do get my original integrand. All right, let's do a little trig functions review. Take a moment and see if you can find the integral, the indefinite integral of all these trig functions. All right. See if you can take the antiderivative of this function. So the inside function here looks like x cubed plus 5. Its derivative is 3x squared. Or I'm actually going to move that dx to the other side. In the integrand, though, I only have an x squared, so I'm going to move 3 to the side with the du. And again, I'm going to write it as 1/3. So that means my integral is really cosine of u. And then my x squared dx, I'm going to replace with 1/3 du. So just again, to clarify that, this yellow is going to be replaced with this yellow. So 1/3 du. Okay, so the integral of cosine is sine u times 1/3. I'm going to put that in front. Plus c. 1/3 sine, replace it with x cubed plus 5 again. Plus c. And again, you can check that its derivative does actually equal this. All right, let's do another one. So this one, the inside function I'm going to use here is cosine of t. Its derivative is sine of t. Du dx is sine of t. So this integral really means, so sine of t dt, oh, that should be dt. I'm going to replace with du. And then this here at the bottom, this is u to the -3rd. Right? It's cosine cubed, but it's on the bottom, so hence the negative exponent. All right, taking the integral, we add 1 to the exponent, divide by the new exponent. -2u squared. So my final answer is -1/2 cosine squared. And again, you can always check by taking its derivative and seeing if it actually equals this. All right, as always, take a moment and pause, see if you can find the antiderivative of this function. So you're trying to look for the inside function and checking that its derivative is part of the integrand. So this next example is a little different. So we're gonna learn a different method. So let's first think about what we would normally do. So I'm thinking the inside function would be x minus 1. So I'll let that equal u. But its derivative is 1. And I have an extra x in my integrand or in my integral that isn't really like accounted for. So let's go back up to the steps and walk through this. We've talked about if the derivative has a constant, that's supposed to say has a constant that is not part of the integral, we can still work with that. So for example, number 31, when you took the derivative, we got 2x, but there wasn't a 2 in the integral. So to replace x dx, we actually need to move the 2 to the other side. We're not going to just replace it with a du, we're going to replace it with a 1/2 du. If your derivative of u isn't in the integrand and it's not a constant, can we rewrite it using u? So let's go back. So we have this x that's not accounted for. Well, x is the same thing as u plus 1. So I can rewrite this integrand, I'm not sure why I'm using purple, integrand as u plus 1 on the top and square root of u on the bottom. And then, sorry, this should be du over dx, which really means du and dx are the same, so I'm replacing the dx with du. So I have this integral now that only uses the variable u. Now I can integrate it because I have a square root u on the bottom. We've done problems like this before where we can separate this into 2 fractions and rewrite it as a power function or as multiple power functions. So I am subtracting top exponent minus bottom exponent because they both have a base of u. So 1 minus 1/2 is 1/2. And then here I'm just moving the square root of u to the top, making it negative 1/2. Now I can integrate. Add 1 to the exponent, divide by the new exponent, which really means multiply by the reciprocal when we have fractions. Same thing here, add 1 to the exponent, divide by the new exponent. And I'm essentially done. I just need to plug in the u now, which is x minus 1. So I have x minus 1 to the 3/2 for both of these u's. You can write it as square root or as a fractional exponent. Either one is fine. It just has to be a positive exponent. Plus c. And you can always check to take the derivative of this and see if it equals your original integrand. You'll probably need to do some manipulating to get it to look like that, but it should be correct. We can actually probably simplify this a little further by factoring out an x minus 1 to the 1/2, but I think I'm fine leaving it as is. All right, this last section is just some additional examples that are included in homework that we haven't seen in notes, in particular exponential functions. So here we have e to the something. So we do know how to find the integral of e to the x. Take a second, think about what it is. It is itself. Here we have a function in the exponential. It's in the exponent. So I'm going to use a u substitution or the reverse chain rule or anti-chain rule. Those are all kind of informal terms. The more standard term is a u sub or a u substitution. So the inside function is 2x squared. Its derivative is 4x. And that's perfect because that's in my integrand. So this integral really means the integral of e to the u times du, right? The 4x and the dx equals du. All right, so the integral of this is itself e to the u plus c. Don't forget your plus c for indefinite integrals. And replacing the u with the term with x is e to the 2x squared plus c. And you can always check your answer by taking its derivative and verifying that it equals the integrand of your original function. Chain rule, that's a 0. And these two values, these two expressions are the same. This next example is not necessarily anything different with regard to chain rule, but we don't know the antiderivative of an exponential where the base isn't e. So we're going to talk about that right now. So take a moment and remind yourself what the derivative of a number to the power of x is. We reviewed this on our last Go formative. It's itself, and then you would also need to multiply by ln of b. If it were e, it would be itself times ln of e, but ln of e equals 1, hence the ln of b part is unnecessary if and only if the base is e. If the derivative of b to the x equals b to the x ln b, that means the integral of b to the x ln b, take a moment and think about what that should equal, dx. So the integral of the answer should be the original function, should equal b to the x. Okay, but I want to know what the integral of b to the x is, not what b to the x ln b is. So if I want to get rid of this ln of b, I can divide it out from the integral. And since this is an equation, if I divide on one side, I also have to divide on the other side. And here is our new antiderivative. It says that the integral of b to the x dx is itself divided by ln of b plus c. So I'm allowed to do this because ln of b is a constant. It's a number. It's not something with a variable in it. All right, so let's do letter B. So it's the exact same concept as letter A, but the integral is not, the antiderivative is not just itself. It requires this divided by ln of b. So again, the u value, the inside function is 2x squared. Its derivative is 4x, and I'm going to move that dx to the other side. So there's that 4x dx right here. So this integral is really 3 to the u times du. All right, we just learned that the integral of a number to a power with x in it, or with a variable in it, is itself divided by ln of b. So kind of like reverse of the derivative, it's instead of multiplying, you're dividing. So this equals itself divided by ln the base. So replacing the u with the expression involving x, replacing it with 2x squared, here is our final answer. And you can always take the derivative and check that it equals this. So it would be itself. ln 3 is a constant, so I just leave it divided on the bottom. And then it should be times ln of 3 because that's what the derivative with a base of 3 would be. And then I still need to do chain rule, which would give me the 4x, and then the ln's 3's cancel out. It's a bit messy, but I do end up with the original integrand. All right, we'll do part 2 tomorrow or next class.